Right, so this problem has to do with comparisons of kinetic energy. So that is where we're going to start, right? We've got before a collision, and we have after the collision. And the kinetic energy before the collision is 1/2 mv squared. And the kinetic energy after the collision is 1/2 mass of the system times v prime squared. This is the mass of one cart because the second cart is at rest before the collision. This is the mass of the entire system. All right. Well, what's the mass of the entire system? The mass of the entire system is 2m because it's two carts. All right. So in other words, what happens here? I've got a cart here with a speed v, and a cart here with a speed v equals 0. And then after the collision, they stick together and they go off as one, which means the mass of our system after the collision is 2m, whereas before it's m. So now our comparison won't be complete until we figure out, hey, how does this v here compare with the speed of the system afterwards? And the key word here is collides, right? So while I've been teaching you and preaching that collides means conservation of momentum. We wouldn't want to start with conservation of momentum because this question is about kinetic energy. But ultimately, conservation of momentum works its way into here. Right? So the momentum of the system before is equal to the momentum of the system after. What's the momentum of the system before? M times V. What's the momentum of the system afterwards? Well, it's 2m's times V prime. So V is twice V prime, or V prime is V over 2. So now if I take that and bring it back up here, now I'm in business. So this V prime becomes V over 2. I have to square that, and now I can make my comparisons. 1/2 times 2m times v over 2 squared. Well, v over 2 squared is v squared over 4 times 1/2 times 2m is 1/4 mv squared. So how does 1/4 mv squared, which is the kinetic energy after, compared to 1/2 mv squared, which is the kinetic energy before? Well, it's 50% of it. Okay, so the key elements to think about with respect to this question are that the explosion occurs up here at the top of the path. Okay, and at the top of the path, it's important for us to remember that the velocity is only horizontal. There's no vertical motion at the top of that projectile, right? And that horizontal velocity is 20 meters per second. As per our vector diagram here, not drawn to scale, right? Because it clearly isn't a 73-degree angle, but 70 meters per second at a 73-degree angle creates an x component of the velocity approximately equal to 20 meters per second. Really, it's like 20 and a half or 20.48, but let's leave it at 20 here to make our math easier. Right? Remember now, this is just an abstract representation of what's happening to the velocity down here. Does not mean that the particle is located up here at the top. The path is this thing right here. Okay, so now, this is a quote unquote recoil collision, and it's a recoil collision that occurs up here. So there is momentum for this thing, right? The momentum before that explosion must equal the momentum after the explosion. Now, stuff goes off in the x and the y, and momentum's a vector quantity, right? So momentum in the y before the collision equals momentum in the y after the collision. Momentum in the x before the collision equals momentum in the x after the collision. So how do we take care of this math? Okay, well, this math, and really the only way, this is a legitimate potential for an AP question. And the only way that this would work out is if one of these two planes cancels each other out, right? And what do we know about the y momentum of this object? The y momentum of that object is 0, which means the y momentum after the collision for the system must be 0. And since we have one object moving upwards with a speed of 10 and the other one moving downward with a speed of 10 after the explosion, those two things already cancel each other out to give us a momentum equal to 0. Which means the y momentum of the third object has to be 0, which means its only motion is in the x, right? And that's what we need to find then, is the x speed of that third object. So since we know the y is already taken care of, then we got to work with the x. So what's the x momentum of the system before the explosion? Well, it's the mass of that firecracker times its velocity, which is 20. Okay, now what about after the collision? Well, it breaks into 3 equal pieces, which means it's got a mass of 1/3 m, and the first one keeps its original speed, same horizontal speed. So the first particle's got that x speed of 20. The second particle has the same mass, 1/3 m, but it's traveling in the opposite horizontal direction at 30 meters per second. So its velocity is -30. And our job is to figure out the speed of the last one. Well, the last one must also have a mass of 3m, and it's got some speed I'm just going to call v prime. Now our job is to figure out v prime. So mathematically, this is 20m equals 20 over 3m minus 90 over 3m plus 1/3 m times v prime. Well, all the m's go away. So I got 20 equals 20 minus 20 over 3 minus 90 over 3 plus v prime over 3. So if I put everything over 3 to make it easy, then I got to multiply this by 3. So really I got 60 equals 20 minus 90 plus v prime. All right, we actually got to backtrack here a little bit, right? I multiplied a little bit too early, right? So this is 30 right here, not 90. So that's 30, that's 30, and that is 30, right? It's 30 over 3, not 90 over 3. Okay. So then I got 60 equals 20 minus 30 plus v prime. So 60 equals minus 10 plus v prime. 70 is my new velocity because of conservation of momentum. Choice C.